Hi, my name is Dave Lang. Today I'll be presenting joint work with my colleagues Luciana Benoiti, Jada Fakrashan, and Siggy Karsten. And we are working with a beta provided to us by a company called Yup. Yup is a mobile-based tutoring platform. What it does is basically matches students with tutors in remote locations. Students can take a picture of their math problem and then they'll be matched with a tutor in a remote location. They will then text message back and forth until they're able to solve a problem. But I think it might be easier to understand if I just show you this GIF. So, student interacting. And what the task we're going to focus on today is predicting the response time of a human tutor's question, a student's response to a human tutor's question. And why do we care about this? Well, we know that one-on-one tutoring has a very powerful effect. Work by Benjamin Bloom found a 2 standard deviation effect in terms of students' learning outcomes. And just more generally, we know that educational platforms are going towards the cloud, towards these digitally intermediated environments. And it's really difficult, particularly because we're counting on all of these other senses when we're actually engaging and teaching on how people are going to interact. So for instance, you get my tone of voice, you get eye contact, you get gesticulation. All of these things don't exist when you're communicating exclusively via text. More generally, another reason why we should care about response time is that it's been shown to be a proxy of student engagement and learning. And just to move the task a little bit further, there's a real precision and recall trade-off in terms of how often a tutor needs to prompt a student. Too much can be stifling or disruptive to a student's own thought. Too little means that they can potentially disengage, or just that the learning rate might be slower than you would desire. More generally, this is kind of an important step in sort of designing educational chatbots. And we also found that, and I'll show you today, that humans aren't particularly good at knowing how long a student's going to take to perform a task. And while this platform doesn't parallelize instruction or do like one-to-many tutoring, I'm imagining that this might be useful in tutoring students. So the questions we're going to focus on today are, can we accurately classify response times as either short or long? So we're just doing a very simple binary classification. We're going to look at what features are predictive of these response times. And we're also going to conduct a weird thought experiment where we actually feed a student's answer into our machine learning model. And we sort of figure out if knowing how a student is going to respond actually improves knowing when they will respond. And lastly, we benchmark ourselves to human-based performance. And Yup, again, was gracious enough to provide us with several expert tutors who were familiar with this platform. So, the data we're working with, we have approximately 18,000 tutoring sessions. And again, this is mainly middle school and high schoolers. And to just give a sense of the scale of these numbers, this comprises nearly 7,000 hours of tutoring. And on the right-hand side here, we have some sample dialogue from this platform. There are a couple of key takeaways that I want you to have here, is that tutors talk in very formal language, whereas students talk in a much more colloquial context. So we see emojis, we see improper spelling, so it's very messy data as a corpus. And we made the decision to classify response times inside either short or long as below or above 20 seconds. And the rationale for that is partly practicality. We wanted to have a relatively balanced class for our machine learning model, so equal amounts below and above this threshold. And we also wanted it to be a fairly simple task for our human raters as well. The other thing I wanted to highlight that is one of the really nice affordances of this type of data is that unlike, say, the work of Art Fraser and Natalie Persons, where they had to rely on human transcribed tutoring sessions, we actually have things like punctuation marks, so we can actually understand the intentionality and the distinction between something that, say, would be an elicitation or a question. In other words, tell me what you got for this problem versus what did you get for this problem. And again, our sort of approaches are we wanted to weight on a macro F1 score. For all intents and purposes, I think you can think of this as just a simple accuracy metric. Do they get it right or wrong? As sort of a dumb baseline, we created a random guessing model, as well as a simple bag of words where we basically treat every word that's spoken by the tutor in a question as a feature. And we also did more complex feature generation as we ran sentiment analysis on the text, so how positive or negative a tone is being used. We also looked at entrainment, so that's the extent that you and I are, or the tutor and the student are aligning in terms of use of function words. So, are you speaking in a similar fashion? You can think of it that way. We also generated more other simple features such as the length of the question, as well as previous vowel terms, so trying to get a sense of what the previous pattern looked like. And again, we had 3 human raters go through and evaluate a subsample of these questions, approximately 300. And what we found was that, first off, surprisingly, humans were not very good at this task. So they were somewhere in between our random baseline and our bag of words model, so they were just only doing a little bit better than chance on average. And more than that, what we also found was that these human raters weren't even exhibiting a lot of agreement. So what this sort of suggests is that this is an inherently difficult task. Our machine learning model, however, produced meaningfully higher accuracy. And what we also found was that complex features really didn't enhance our model. So things like sentiment and entrainment didn't. And part of the reason why I think that might be the case is that sentiment analysis is very specific to your training dictionary, and words, particularly those related to math, often have different connotations than we're used to seeing. So for instance, obtuse, if you put it into your standard sentiment classifier, it means you're stupid. In geometry, it means it's a type of triangle. But what we basically found was that throwing in all of our simple features really enhanced our model. And what that's then sort of made us think, well, maybe we're not capturing complexity. So we thought, how could we do this with, say, a neural model? And we took a fairly standard architecture. We did we layered fast text word embeddings through an LSTM and through a sigmoid activation function. What we found, we did some hyperparameter search, but largely we found our results were invariant. And so what does everyone think? Do you think a neural network is going to do better than some standard ML approaches? Yay? Nay? The short answer is not really in this case. We found that our neural network performed roughly with the same accuracy as our sort of standard machine learning model. We then conducted one additional exercise, and that's where we not only fed our ML model into the tutor's question, but also the student's response. And what we found was that we had even higher accuracy. We also saw that humans exhibited the same behavior, that they became more accurate once they knew what a student's response was. And in addition to that, we found that they had higher levels of inter-rater agreement. That being said, we found that our sort of standard ML algorithms outperformed human raters even under this condition. That being said, our model did have some clear blind spots. One of which was that this task was inherently difficult, that there's a lot of repetition that occurs in tutors' questions. Like, what did you try? Are you still with me? All of those things occur in very different and distinct contexts, and therefore it makes it really hard to generate any model when you basically are feeding classes that are both short and long. We also found that sort of politeness strategies tend to misfire, that our model, when collaborative language was used, that students tended to respond faster than our model anticipated. And finally, we found that questions involving cheating. So for instance, is this pertaining to a quiz or is this just your homework? Those also tended to misfire in terms of our model accuracy though. And that's consistent with what we know about human psychology. My interpretation is that a machine learning model thinks that this is a very simple yes-no question, but a human knows that the student then needs to think about, are they being honest, are they being clear, are they being transparent, and there's a much more complex thought process that needs to occur on behalf of the student. So the key sort of takeaways from this exercise, we found that the standard ML algorithm beats humans at this task. We also find that providing the student response string also increases our accuracy in both our ML and human rating model. And what that does suggest to me is that natural language generation could actually be really useful in terms of even improving this type of response time model. So for instance, as I said before, if I know what you're going to say, I know when you're going to say it. And finally, we're hoping to improve model accuracy on this a fair bit, but I think the next step is going to be to try and embed this in a learning platform and actually see how this service works when you pair it with a live tutor. Do they actually rely upon this? And does it maybe reduce cognitive load so that they can focus more on teaching rather than anticipating what the student's going to do next? Thank you. If you're curious, we presented an earlier version of this at ENLP, and the link is right up here.
Yeah, so were the human raters given features, or did they have to do feature extraction from the raw conversation?
They were given all of the same we did a few different cases and context, but generally we gave them the same question strings as well as no, we didn't do something like show them word embedding vectors and then ask them to predict. We still showed them the raw text.
Right, so because then it's a little bit unfair because a human being has actually extracted the features for the machine learning model, whereas a human rater, as a human rater, I have to read the text and have to sort of extract the features and then make a decision based on it. So it's just, I'm just wondering if you could do the test where you actually given the row of data that you have for the raw data.
So we included the pattern, and that's all that we fed into the machine learning model. So we showed basically the 5 last utterances in the conversation, as well as everything involving response times. So, yes?
It's on a similar note. So sorry if I missed this, but were the humans given all the training data that the computer was given to kind of understand people's interactions with this particular texting system?
So they were given a small training and validation sample, and these are tutors who work on the platform, so they are actually very embedded and knowledgeable about the system.
Okay, great, thank you.
Yes.
What's the operational application of predicting response time? Are you trying to select between prompts that have short response times, or is there some other application of this prediction?
Well, the big sort of motivation for this task is because this type of environment is fully instrumented. You don't know, say I'm working productively with pen and paper alongside the tutor, or if they've drifted off altogether. So the idea here is that if we can train a model to sort of know that this is a short yes/no question, then if the tutor hasn't heard back from like within 20 or 30 seconds, the tutor knows, okay, they should have been able to answer this by now. I should try and re-engage them. That's the ultimate goal.
You mentioned that one of the areas where the model still required work was whenever the check for understanding, are you still with me, was presented by the machine, or by the tutor. I was wondering how close are models to moving from a statement like that to something like getting students to summarize their thinking and then making a judgment based on the output of the student?
I think the short answer is very far away. It certainly is what I would like to see this literature going towards. I think one of the big challenges is that they're very small training corpuses. I think I've got one of the larger ones having about 7,000 hours to work with. But often what people were doing before this was just transcribing something like 40 to 100 hours of human tutoring.
So going back to the use case that you were just mentioning about response times, do you have a sense of if there's a slow response time, how much of that is like actually specific to the question and how much are external factors? I mean, when people text, they're usually, even if they're in a tutoring session, they may be doing other things. That's not going to be in your model, and that could really confuse things if someone gets like a message from their friend during this session.
No, that's a really good point. I think part of the reason why I really like and value this data set is, again, going back to my earlier statement about what often human transcribed sessions aren't capturing. Everything that's being reflected in this type of event, in this type of medium, is intentional communication. So I think, again, you're absolutely right. There are quite a few issues here in terms of why responses are going to be noisy. But I think it's still somewhat useful for just building a dumb rule that perhaps might work better than a tutor's own intuition.
I think we still have time for one last question. We set up 40 seconds. If no, let's